Okay, let's get started, please. So we were talking about sequences in metric spaces, sequences in complex numbers, and sequences in Euclidean spaces. And now we're going to talk about something called subsequences. Subsequences. Okay, so subsequence is what you think it is, right? You have some sequence, and then a subsequence is basically some selection of those those items. Okay, in increasing order. The only thing that's tricky is writing this down. Writing down what you mean mathematically. So here's how we describe a sequence. You know what a subsequence is, but here's the definition that will make you think you don't know what it is. Okay. So but trust yourself, you actually do know what it is. Okay. So you have P sub n a sequence. You start off with a sequence, and you have let n sub k from k equals 1 to infinity be a strictly increasing sequence in the natural numbers. Okay. So then we call P sub n sub k from 1 to infinity, a subsequence of P sub n. Okay, now this looks kind of mysterious, but all it's saying is that these are your new indices, right? These are the indices that you choose. So I'm starting off with some sequence. Let's say that P sub n is my sequence 1, 2, 3, 4, 5, 6, etc., whatever, right? And I'm going to let n sub k be say 2k, right? As k goes from 1 to infinity, right? Right? And so P sub n sub k is going to be the sequence, right, with those indices, right? It's going to be the selection of those guys, right? It'll be 2, 4, 6, 8, etc., etc. Right? So it's saying let's take the second guy, the fourth guy, the sixth guy. Right? So you have this increasing sequence, and you use it as the indices of your new sequence. Right? Right. So this is basically your new index sequence. Okay. Yeah, Abel.
It doesn't have to be infinite, though, right?
No, you want it to be infinite.
No, I mean the subsequence.
The subsequence you want to be infinite also.
Oh.
Yeah. So all these are all infinite sequences. Okay. So so one remark is that the full sequence, the full thing is still considered a subsequence. A subsequence. Right, because your strictly increasing sequence could be just 1, 2, 3, etc. Right, you could be n sub k could be just k. Right, in that case, you're going to recover your whole sequence. So the full sequence is considered a subsequence of itself. Okay. So another remark is that if P sub n converges, the sequence converges if and only if every subsequence P sub n sub k converges. P sub n converges if and only if every subsequence converges. Okay, yeah, I'm fine.
Isn't that trivial because the full sequence is a subsequence?
So one direction is trivial, right? If I say every subsequence converges, and I just said that the full sequence is a subsequence, then of course the sequence converges, right? So that's definitely trivial, right? Every sequence, if every subsequence converges, then certainly, you know, the subsequence consisting of the full sequence converges. Okay, so that we don't have to worry about, right? So maybe take 1 minute and convince yourself that you know how to write the proof of this. Okay. Okay. The only tricky thing is writing it down. This is not. Yeah. The only tricky thing is writing it down. So see if you can write down the argument showing that. So let's put it this way. Suppose P sub n converges, and let P sub n to k be a subsequence. In other words, n sub k is a strictly increasing sequence, right? And let's show that P sub n sub k converges to the same thing. So, sorry, I forgot to say this. It'll converge, of course, to the same point. So just as a writing practice, see if you can write this down. Every time I hear a student ask, isn't that trivial? I always hear my old professor back in college replying, well, if you're omniscient, then everything is trivial. Yeah, there was one very bombastic classmate of ours who would always be like, well, professor, isn't that trivial? Okay, let me just write it down for everybody. Okay, so right, we want to show that there exists a capital K such that if K exceeds this capital K, then P sub n sub K minus P where are we? We are just in some such that the distance between P sub n sub k and P is less than epsilon, right? So sorry, that's not right. We want to show that given an epsilon, there exists a case such that this happens. Okay? Okay. And you say, well, since P sub n converges to P, we know there exists some n such that if n exceeds n, then distance of P sub n to P is less than epsilon. Right? And since since n sub k is increasing, we know there exists a k such that if you're bigger than k, then n sub k is bigger than that capital N. Right? Right? So if k exceeds that capital K, we know that n sub k exceeds n, but that tells us that the distance between P sub n sub k and P is less than epsilon. Right? So we're done. Yeah, all right.
I don't understand how you concluded that there exists a case such that k greater than k implies n k greater than n.
Well, n sub k is increasing, is strictly increasing, right? N sub a is strictly increasing. And so we fixed our epsilon, and from the convergence of p sub n, we pull out this capital N. Okay, we know that as long as these guys, as long as the index is bigger than that capital N, then everybody's within epsilon of p. Okay. But we're dealing with the subsequence, right? So you say, okay, well, the subsequence is these things with, how do we know that this, so there's going to be some, so here's our sequence, and there's some capital N, and past that capital N, we're good. Okay. Right, but since the indices are strictly increasing, we know that eventually they're going to get bigger than n. Right, that's all I'm saying here. Right, there's a time past which my indices are all bigger than that good time. Right, so I found the k past which, as long as this little k is bigger than that, then all of my indices are bigger than this n, and so they're all the p sub n sub k's are within epsilon of p. Okay. So this is just an exercise in writing. Okay. Okay. So any questions about that? Any questions about that? Okay. So so let's do sequences in compact spaces. Okay. And this will give you some sense of why we are interested in subsequences. Okay. So you have a p sub n, a sequence in X, a metric space. And the claim is that X compact implies that there exists a convergent subsequence. Of the p sub n's. Okay. Whenever you have any sequence in a compact space, then there exists a convergent subsequence. Yeah.
Can we do the contraposition of that and say if every subsequence, if we define divergence to be non-convergence, then when every subsequence diverges, does that mean that the whole...
The contrapositive would be there exists one divergent subsequence.
Oh.
If there exists one divergent subsequence, then the original guy must have diverged.
And if the first thing, like if the whole thing diverges, then there exists at least one thing that diverges in it.
If the
Whole sequence.
If the sequence diverges, then
there exists at least one thing.
yeah, it would be at least one subsequence, but that would be the sequence itself.
Itself, okay.
Yeah. Yeah, that might be the sequence itself. I mean, it is at least the sequence itself. Okay. So if you have a sequence, if you have any sequence in a compact set, then there exists a convergent subsequence. And the proof of this is kind of funny. You say, well, consider E the range of your sequence. The range of your sequence. Right? These guys might repeat, right? Some of these p sub n's might be the same, right? The p sub n's could be all the same point. Okay. So there are two possibilities. Right, case E is finite. Right? So here's your space X, and here's your timer, your ticker. Right? And suppose there are only a finite number of outputs, right? So like P1, P2, P3, P4, P5. Right? There's only a finite number of outputs. Okay. Well, in that case, you're done, right? Because why? How do you construct your convergent subsequence? Suppose I have like P5. P5 is this. Suppose I have only 3 outputs, right? I have P6 here. I don't know. P7 is this guy, and then they all end up on this P7, P8. That's P8, P9, P10, etc. They all end up here. Well, my sequence would be 2. My subsequence, my index sequence would be 2, 4, 6, 8, 9, 10, blah blah blah. Right? I would just stick with this guy, right? So you see what's going to happen. I'm going to choose the one that gets hit infinitely many times, right? One of them has to get hit infinitely many times because there's only finite many outputs, right? So, right, by pigeonhole principle, you know that there must be infinitely many pigeons in one of the holes, right? Right. So one of the outputs, right, must be hit infinitely many times. Right. Right. In other words, we can construct a subsequence P sub n sub k, where they're all the same, right? P sub n, they are all the same. Okay. So that's you're done. Yeah, Aria.
And I guess even if you had like 3 outputs and it kept alternating between the 3, you could still pick one of those.
Yeah. You just choose. When we say one of the outputs must be the same, I mean, that's all you need, right? You could, to be maybe more vernacularly precise, you would say at least one of the outputs. Right? Choose one of them, right? Right. Okay. Sorry, I thought you had a question. No. Okay. Okay. So then the second case is that E is infinite. Right? So the outputs form an infinite subset. Right? But in that case, you got an infinite subset of a compact set. Right? You have an infinite subset of a compact set, and you know that. What do you know? It's compact, so you have an infinite subset, and so, no, you guys are throwing out the wrong words. You're throwing out the sort of related words, but what word am I looking for? I want to make a sequence, remember? I want to make a sequence. Nope. Nope. No. There's this one song that my kids listen to, and there's a child listening to her dad sing incorrect statements, and she starts going, no. It's the elephant song, do you know this? Anyway, the word I'm looking for is limit point. Right? You've got an infinite subset. You've got infinite many points in a compact set. We know that there must exist some limit point. Okay. So, right, since x is compact, we know there exists some limit point p of n. Okay. Right. So there's a limit point p, and we know what that means, right? we know that in every neighborhood there exists every punctured neighborhood contains some point in E, right? In fact, contains infinitely many points of E. So the only thing is to construct the sequence properly. You say, okay, let's say that, so we choose n sub 1 such that the distance from P to Pn sub 1 is smaller than 1. Okay. So what I'm going to do is I'm going to choose shrinking radii. Right? My first radius will be 1, my second will be a half, etc., etc. Okay. So choose my n sub 1 such that this is true. Choose n sub 2 such that the distance between P and P sub n sub 2 is smaller than a half, and n sub 2 is bigger than n sub 1. Right? I have to do that in order to get an increasing index sequence. Right? Why can I do that? How do I know that's possible? Well, I know that there's infinitely many guys inside this punctured neighborhood. Right? So certainly somebody's going to have an index bigger than n1, right? Because there's infinitely many of them. Right? Et cetera, et cetera. Okay, and then you choose, n sub 3 bigger than, so the distance is smaller than a third, and the index is bigger than n2, and so on and so forth. But it's good to throw out a lot of ideas, actually. So I shouldn't say no. Yeah, it's actually better to have a lot of ideas rather than to be sort of always saying no. Okay. Make sense? Everybody all right? Okay. So remark that what that tells us is that any bounded sequence in Rn has a convergent subsequence. Right? Because if you're a bounded sequence, you sit inside some compact set, right? You sit inside the closure of that bound, right? That bounded set. Well, then you're an infinite sequence in a compact set. Right? This is called the Bolzano wire stress. Bolzano wire stress theorem. I recommend the elephant song for people who like kind of amusing, cute things. I guess you'll always be too old for it. Okay. Next, really important idea, the notion of a Cauchy sequence. Okay, so this is one of the central ideas. Okay, so here's the definition. So again, you have a sequence in X, a metric space, and here's the definition. If given any epsilon greater than 0, there exists a time such that if n and m exceed that time, then the distance between p sub n and p sub m is less than epsilon. Then we call p sub n a Cauchy sequence. Cauchy sequence. Okay, so this is saying that given any epsilon, there's a time past which everybody is within epsilon of each other, right? Any pair of points, there's a time past which any 2 points are going to be within epsilon of each other. Okay. The previous definition of having a limit was there's a time and a point, right? And everybody is within epsilon of that point, right? Okay, and this is slightly different. This is saying there is no point, right? But there's a time past which everybody is within epsilon of each other. All pairs are within epsilon of each other. Okay, and you can see that having a limit forces you to be a Cauchy sequence, right? If your sequence converges, well, then it's going to be a Cauchy sequence, right? Because everybody's going to be close to that point, or they're going to be close to each other, right? So so it's easy to see that if the sequence converges to some p, then the sequence is Cauchy. Right? Because, right, given epsilon, we know that there's some time such that if you're past that time, the distance between p sub n and p is less than a half. Right? By convergence, right? By convergence. By convergence, right? Well, but then that means that if 2 guys are past that time, then the distance between them is smaller than epsilon by the triangle inequality, right? Because this is smaller than the distance, the sum of the distances to that point. So if you are a convergent sequence, then you're Cauchy. It's not true, the opposite is not always true. You could be Cauchy and not convergent. Okay, and the sort of standard example is that if you look at p sub n being 1 over n in R plus, well, that's a Cauchy sequence, but it doesn't converge to anything because there's the hole there. Okay, so your space has a hole in it. Okay, but this idea of being a Cauchy sequence is really crucial, right? If you don't know what a Cauchy sequence is, then I hate to say that you're nothing, but it's sort of like that, right? Yeah. Okay. Okay. So a more intuitive idea. Okay, so we use the notion of a diameter. So you have some subset of a metric space. So this thing is, as usual, metric space. You have some subset of a metric space, and what you do is consider the set of all distances. Okay. You consider the set of all distances between pairs of points. Okay. So you've got your metric space, and you've got some subset. You've got some subset, and you look at the set. You look at all pairs of points, and you look at all distances between these points. Right. Whatever. Anyway, you look at all pairs of points and the distances between those points, and you let, so this thing is a subset of R, right? Because the metric maps into R, right? The metric gives you some real numbers, right? So define the diameter of E as the supremum of S. As the supremum of all these distances. And it may be infinite, right? It could be infinity, it could be infinite or it could be finite, right? If it's infinity, it means that there's points of arbitrarily large distances, right? Okay. Okay. So remark that coming back to the sequence, returning to, so let P sub n be a sequence, and let E sub n be the tail, Pn plus 1, Pn plus 2, etc., etc. Okay, be the tail end, be the tail elements, the tail of the sequence. Okay, right. It's a sequence starting from the nth term. Okay, so it's just you've got some sequence, and you get rid of the first n minus 1 elements and the tail. So this E sub n means the tail. Okay. Then it's pretty clear to see that E sub n is Cauchy. It's the same thing as saying that the limit of the diameters of the tails as n goes to infinity is 0. Right? I hope you see that that's exactly the same thing as being Cauchy, right? Because Cauchy says that given any epsilon, you can make distances between points smaller than epsilon, right? And for the limit of the diameter of the tail to go to 0, well, that means that given any epsilon, you can find an n such that all the tails past that point, all the tails past that point have a diameter less than epsilon. But a diameter less than epsilon means that the distance between any 2 points past that n is smaller than or equal to epsilon. So I mean, it's about the same thing. It is the same thing. Okay. So this is. Does everybody see that? Right. So being Cauchy means that the diameter of the diameter of the tail shrinks to 0. Okay. 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 So we're going to use this notion of diameter. At least Rudin seems to like this notion of diameter, so we're gonna use it. So here are some facts about the diameter. So facts about the diameter. First off, that the diameter of the set and the diameter of the closure of the set are equal. Okay. And second fact, if you have K sub n a sequence of nested sets in X, okay, you've got a sequence of nested sets in X. If the Kn are all compact and the diameters of the diameters of the K sub n go to 0, then the intersection of these sets consists of a single point. Okay. The second one is pretty easy. I'm sorry. The second one is pretty easy. Let's do the easy one first. Okay. So, what do you know? You've got a bunch of nested sets and they're compact. What do you know about their intersection? You've got nested sets, right? And they're compact, right? Right. What do you know about the intersection? We had some property earlier. Anybody remember? So you notice that if you intersect any finite number of them, you're going to get something, right? Mm-hmm. Right. And so when you intersect all of them, you still get something, right? So this was this thing that we showed about compact sets, right? That if they satisfy the finite intersection property, then the infinite intersection is non-empty. Okay. So. Right. So proof of 2 is that since they satisfy, since the K sub n are compact and satisfy the finite intersection property, we know that their infinite intersection is non-empty. We know that the infinite intersection is non-empty. Okay. So the only thing we have to show is that the intersection consists of a single point, but if it consisted of 2 points, then the diameter would not go to 0. Right? Right? If it consisted of 2 points, that means that every one of these sets contains those 2 points. But in that case, the diameter is not going to go to 0. Okay. So, and if the intersection had 2 points, then the diameter cannot go to 0. It's going to be bigger than or equal to the distance between those 2 points. For all n. Okay. And so the limit would not go to 0. Let's do the first one. Let's do 1. Okay. So that the diameter of the set and the diameter of the closure are the same. Okay. So it suffices to show that the diameter of the closure is less than or equal to the diameter of the original. Right? You know that the diameter of the closure is greater than or equal to the diameter of the original, right? Because you're just throwing in more stuff, right? So the only thing that you need to do is show that it's less than or equal to, right? Okay. So here's how we do it. You say, pick any 2 points, P and Q, in E bar. Pick any 2 points in E bar. Being in E bar means that you're either in E or you're a limit point of E, right? Okay, so so we know that given any epsilon, there must be P prime and Q prime in E such that the distance between P and P prime is smaller than epsilon over 2. The distance between Q and Q prime is smaller than epsilon over 2. Right. being in E or E prime, you know, if you're in E, then this P prime, if P is in E, then P prime could be P. You can just take it to be the same thing. If P is a limit point, well, you know that there's somebody within epsilon over 2. Right? There's somebody close to you. Right? Okay. But what does that tell you? That tells you that the distance from P to Q is controlled by the distance of P to P prime plus the distance of P prime to P prime to Q plus the distance of Q prime to Q. I should say less than or equal to, by the triangle inequality. Right, which is less than epsilon plus the distance from P prime to Q prime. Okay, what does that tell you? That if you take any two points in E bar, well, there's some points in E where if you add on this little epsilon, you get something bigger than the distance, bigger than the distance between these 2 points in E bar, right? But what does that tell you? That tells you that the diameter of E bar must be less than or equal to epsilon plus the diameter of E. Right? Because you take the supremum over this thing, right? And you know that it's controlled by this. Okay. Right? But this is true for any epsilon, right? So this is true for any epsilon. So that tells you that the diameter of E bar must be less than or equal to the diameter of E. Right? The only way that could be true for any epsilon would be this. Once I was in China, and a student said, "Hey, Professor, take a picture with me." I said, "Okay." I took a picture, and immediately he did something to it that put some ears and like strange things on me. And
how do we know that the diameter of E is less than or equal to the diameter of E bar?
Well, E bar is E with other things thrown in, right? Right. So remember what E bar is, right? E bar is E with E's limit points thrown in, right? So the diameter of E bar is definitely bigger than the diameter of E, right? Because it has all the points that are in E and more.
It's not necessarily bigger, it's just
I'm sorry, bigger than equal to. All right.
So to get to the final statement where we say diameter of E bar less than or equal to epsilon plus, you said we took the supremum of both sides?
Well, so it's rather this. You take the supremum on the left side, okay, and you get the diameter of E bar, right? So let me say it this way. So this thing is always less than or equal to epsilon plus the diameter of E. Okay. Now I take the supremum of the left side. Okay, and I say, okay, well then this thing is less than epsilon plus the diameter of E.
Okay.
Sorry, that was wrong.
Thank you.
Okay. Other questions? Okay, let's go on. Let's see. Okay, so just a bit of language. Axiometric space. If every Cauchy sequence converges, in X, we say X is complete. Okay, X is complete. Okay. So what this is saying is that convergence and Cauchy sequence, convergent sequences and Cauchy sequences are the same thing in such spaces, right? So we already saw that if you're convergent, then you're Cauchy. And in some spaces, if you're Cauchy, then you're convergent also, right? Those spaces where the two notions are the same or equivalent are called complete spaces. Okay, so for example, Q with the standard metric is not complete. Right? Because it has holes in it. Okay, so let me see if I can do one proof. If X is compact, X is a compact metric space, then X is complete. Any compact metric space is a complete space. Okay. Okay. So we want to show that every Cauchy sequence converges, and so let P sub n be a Cauchy sequence. Okay. And let, as before, E sub n denote the tail starting from the nth term. Okay. So we know that that the limits of the diameters of these tails goes to 0. Now, consider the closures of the tails. Consider the closures of the tails. Each E sub n closure is compact. Why is it compact?
It's a closed subset of the complex.
Very good. Yeah, right. Our space is compact. If we close the set, then this is going to be compact, right? And so, the intersection of the tails, the closure of the tails, the infinite intersection of the closure of the tails, is going to consist of a single point, right? Because they're nested compact sets. And we said just now that the intersection is going to consist of a point. Okay. Okay. So now, given any epsilon, choose n naught such that if n exceeds n naught, then the diameter of En bar is less than epsilon. Right? That tells us that the distance between P sub n and P is smaller than epsilon for all n bigger than n naught, right? But that's convergence, right? So Pn converges to P. Maybe just to be safe, let me put this epsilon over 2. we know the tails, the intersection of the tails is a single point, right? We want to show that we can find a time past which everyone is within epsilon of that single point. So you say, okay, well, I know that the diameters shrink to 0. I know the diameters shrink to 0, so I can choose a time past which the diameter is smaller than epsilon over 2. But that means that all the points, the distance from P, in that tail are smaller than epsilon distance from P. But that's what we're wanting. Okay, that's it for today. I do have homeworks to return. Sorry. If you don't want to stick around, that's fine. If you want to stick around, that's also fine.